Hello friends, I welcome you in this particular session when we are going to talk about one of your core subject for electrical engineering as far as the GATE examination is concerned. All those candidates who are seriously preparing for GATE 2026 examination, this session is going to be extremely important for you if you are from electrical engineering, because we are going to talk about power system, which is one of the core subject for electrical engineers. So all the candidates who are joining me live, just quickly confirm your presence in the comment section and tell me whether my audio, visual quality, everything is clear so that we can start with the session. So friends, as you have already seen a lot of sessions by different faculties, you must be knowing that Geeks for Geeks has recently started with EC and electrical as a department, as a branch, and we have started some courses also. And in that direction, we have planned number of initiatives which are completely free of cost on YouTube till your GATE 2026 examination. So you must be enjoying a lot of sessions. Okay, so let me just once check the audio and visual quality. I hope it is clear. Everybody please confirm in the comment section. Audio, visual, everything is clear. Good evening everybody. Welcome to the session. So before we start the session, it is important that let me just introduce myself. If you know me better, then you will be able to learn from me in a better way. So as you can see on the screen, my name is Ashutosh. I have passed my MTech in 2010 from IIT BHU. And since then, I have been mentoring students for different examinations like UPSC, Engineering Services, GATE, and PSUs. Basically, I'm from electrical engineering. I teach some of the core subjects of electrical engineering like electrical machines, power system, electromagnetics, and many other subjects. I also teach some of the non-technical subjects, especially engineering ethics. So this is my background. Now let us talk about the subject first. If you talk about power system, let us first understand what type of questions you can expect and what are the areas which you can say that these are the most probable areas from where questions can be asked. So if you see, the basics of power system lies in understanding the power. When we talk about the power, so it is the very fundamental part of your subject power system, fundamentals of power system. When I say fundamentals of power system, as I told you, you have to understand that what we mean when we say power. When we say power, we talk about active power, we talk about reactive power. We also talk about single phase power, and we also talk about three phase power. Okay. Then we talk about single line diagram. We talk about impedance diagram or reactance diagram, impedance diagram or reactance diagram. Okay. And then we talk about one more important tool, that is per unit system. That is per unit system. Now, every year, if you have seen the previous year papers, you must be knowing that if you see the previous year papers, especially in 23 or 24, you can say there were two simple direct questions from this particular area. And this is something which is so basic and fundamental. If you are not very clear in this particular concept, it will be a mix of theory and questions, Ashish Raj. It will be a mix of theory and questions. We'll discuss some important concepts, then we'll do some related questions also, so that you get a complete idea how to deal with the questions in the examination. Okay, let me just first make you clear that what this subject is all about. What are the important areas from questions are going to be asked and how you are going to approach this particular subject in the examination. So as I told you, 23 or 24, there were two questions which were directly asked from this particular area, single phase or three phase power. In terms of active power and reactive power, they have asked a very basic question. If you're not aware with the per unit system, you will not be able to solve the questions related to the later chapters. You will not be able to solve the questions related to fault analysis. You will not be able to solve the questions related to load flow problems. any particular chapter, you will not be able to solve the problems, even in machines also, electrical machines also, if you don't understand the per unit system. I hope you are able to follow me. Ashish Raj is saying, sir, actually I have not done stability, so I was concerned a bit. Don't worry, you just follow these sessions, okay? We are going to cover complete power system in approximately 2 to 3 lectures. Today we don't have enough time. Okay, it was supposed to be scheduled at 6 p.m., but because of some reasons, it was scheduled 8 p.m. So there is a limit beyond which we cannot go in terms of time. So we'll be having maybe 3 sessions for power systems. So tomorrow's class is going to be from 6 p.m. onwards, okay? You just follow these sessions, and every particular chapter, whether it is stability or any other chapter, we are going to cover it up to the requirement of GATE examination, okay? Now you understand, after this, the next thing is transmission line. If you see, transmission line is one area, whether you talk about the short transmission line, whether you talk about the medium transmission line, whether you talk about the long transmission line, the most probable area from where questions can be asked is that they can ask you questions related to the ABCD parameters. They can ask you questions related to the voltage regulation. Okay. So these are some of the areas. These are some of the areas from where questions can be asked from the transmission line part. There are some other aspects also from where questions can be asked. They can ask you questions related to, the line constants, calculations. Okay, when we talk about the line constant calculations, basically we talk about R, L, and C calculations. That is the resistance, inductance, and capacitance of the transmission line. From this particular area, questions also can be asked. In this respect, they can ask you questions related to the geometrical mean distance and the geometrical mean radius. If you see, I think 2024, there was a very small question on GMR. Okay, that was the stranded conductor question where there was a steel wire. So that is also what we are going to discuss. Apart from this, the third topic from where questions can be asked is the performance analysis of transmission line. Okay. Then we have the transient analysis of the transmission line. You can expect questions from this area also. Then we have voltage and power factor control. Now this is one area again from where you can expect questions, voltage and power factor control. Okay. They can ask you some basic questions like reactive power compensation. They may ask you the static compensation. They may ask you the dynamic compensation also. Okay, so this part is also important. Then we have HVDC, high voltage DC transmission. Okay, then we have insulators. When we talk about insulators, we are generally talking about the overhead line insulators. And then we also talk about the underground cables. There is one chapter which has become important in the recent year. If you see the previous year questions, you will see that they are asking questions from the distribution also, power distribution system. So you can expect one small question from power distribution. Maybe AC distribution or maybe DC distribution. AC distribution or DC distribution. Okay. Then we have load flow analysis. Because the GATE examination is going to be objective examination. So if they are asking the theory-based question in terms of MSQ or any other type of question, MCQ, then you have to read all the methods, all the 5 methods. But most of the time they are talking about questions based on load bus. or size of the Jacobian matrix. Size of the Jacobian matrix. So these are some of the most important or the most probable areas from where questions can be asked. Coming to your topic, power system stability. Power system stability is one area we have seen in previous year that number of questions are asked, whether it is steady state stability or transient stability. Okay. They are asking questions based on critical clearing time, critical clearing angle. They are asking questions related to the equal area criterion also. Okay. Equal area criterion. This is one more important chapter. Equal area criterion. From here also questions can be asked. Then we have fault analysis. One more important part from where questions can be asked. Then we have protection system. When we talk about protection system, we generally talk about theory of circuit breaker and relays. This is again one area from where the possibility of getting questions is very, very high. Then we have economic load dispatch. You can say as the last chapter, as far as the GATE examination is concerned, there are some more chapters or topics to be covered if you go for the subject, but as far as the GATE examination is concerned, these are the areas from where you can expect questions. Okay. Now, before we proceed, let me just give you some idea about the recent courses which have been launched on the Geeks for Geeks platform for EC and electrical students. So we have launched basically two types of courses, 1 year course for GATE 2027 and the 2-year course for 2028. So you can go to the Geeks for Geeks platform and you can see these courses, what are the important points, what are the main characteristics of these courses and how these courses are going to help you in achieving your goal. So this is all about the courses we have made live for EC and electrical students. Now let us start with the very basic part of our subject, that is power system. So we'll first talk about power. Now when I say power, you please understand in terms of when we say power, okay, just give me a moment. Just give me a moment. Just give me a moment. Okay. So when we talk about power, in case of our subject power system, so actually we are talking about complex power. Actually we are talking about complex power. Complex power we also call as apparent power. Apparent power, or more general you can call it total power. Total power. So basically if you talk about power, power we are defining as the real power and the reactive power. This is what we call as complex power. This is what we call as real power. And this is what we call as reactive power. So just by going this particular equation, it's a complex equation. So if you see this equation you can draw in terms of a power triangle. In terms of a power triangle. So you can define this is the real power, this is the reactive power, and this is the total power or the complex power. This particular angle we are defining as the power factor angle. This particular angle we are defining as the power factor angle. So if you ask me, sir, S we can define as the under root of P square plus Q square. If you ask me, sir, what is P? We can define it as S cos phi. What is Q? It is S sin phi. Okay. And if you want to relate P and Q directly, that also you can relate, because you can write Q is equal to P tan phi. Now you want to imagine that in GATE 2024, if I am not wrong, GATE 2024, there were 2 questions directly from this particular equation. There were 2 questions directly from this particular equation. Everybody just tell me in the comment section, are you able to follow me? Duration of the class is, in general, you know that all these marathon sessions, the total hours allotted are going to be 8 to 10 hours for one subject, okay? 8 to 10 hours. All the candidates who are live with me, just quickly confirm, are you able to follow me? Just quickly tell me in the comment section. Now, before we proceed, it is important for us to understand that what do we mean when we say real power and reactive power. It is important for us to understand. What do we mean when we say real power? See, it is that part of our total power or the apparent power which can be finally put to the useful work. Which can be finally put to the useful work. It means if you see the fan in your room, it is running because of this real power. Work output can only come from real power, not the reactive power. If you see the bulb or the LED shining in your room, it is because of real power, not because of reactive power. So any useful work output you can get if you have real power. Sir, how we define reactive power? Sir, how we define reactive power? Reactive power is a power or the part of a complex power, the part of the total power which cannot be put to the useful work. Cannot be put to the useful work. Now, if we go with this definition, the very fundamental question arises in your mind, then sir, why do we need reactive power? Why do we need reactive power? Now, if you see, if we talk about transformers, if we talk about electrical machines, you can talk about any electrical machine, okay, any electrical machine, or many other, you can say, devices. They are not going to work or function without this reactive power. Sir, why? Because the electrical system and the mechanical system are coupled using the magnetic coupling. Have you seen? Have you seen a motor? Have you seen a generator? Mechanical power is being converted to electrical power is being converted to mechanical power, but the system which connects these two different systems, mechanical system and the electrical system, is nothing but the magnetic coupling. This magnetic coupling is only possible because of this reactive power. So your transformers are not going to work, your machines are not going to work, and various other devices are also not going to work if you don't have reactive power. It means if you don't have transformers, you cannot transfer electrical power from one place to another place. Because even if you talk about the HVDC, high voltage DC transmission, still you require transformers. Still you require transformers, because we always go for the maximum possible voltage which we can have practically to transmit electrical power. We will discuss why we go for that much high voltage. The most simple answer is the real power which you can transfer is directly proportional to the square of the voltage. So as you increase the voltage level of your transmission line, the amount of real power which you can transfer over your transmission line is going to increase. And that is what we want, to transmit more and more electrical power. But Your transmission line is not going to work if you don't have transformers. And your transformers can only work if your primary and secondary high voltage and low voltage windings are magnetically coupled. This magnetic coupling requires the reactive power. I hope it is clear. Everybody just tell me in the comment section, are you able to follow this? And please share this session among your friends. Okay, it's a healthy competition. Okay, don't become the chatur of three idiots. Okay, sometimes good deeds also work. Is that clear? Now, coming back. So we are defining the complex power as the combination of real and reactive power. Sir, how we are defining the complex power? We are defining the complex power. We are defining the complex power as S is equal to V into I complex conjugate. But this equation you can apply if the voltage and currents are given in the polar form. If the voltage and current are in polar form. Sir, what is polar form? We don't understand polar form. If you write voltage as voltage magnitude e raised to the power theta 1 and your current as current magnitude e raised to the power j theta 2. It means there is some magnitude and there is some phase angle. If you have these two properties, it means you are writing your voltage and currents in the polar form. So if you have voltage and currents in this polar form, to find the complex power, we'll use this formula, voltage multiplied by the complex conjugate of the current. Now there is one more confusion among various students. Sir, why we are taking the complex conjugate? One reason. Another question is, even if we are taking the complex conjugate, why we are taking the complex conjugate of the current? Why not the voltage? So let us answer these two fundamental questions. The first question is, why conjugate? Now you please understand, when we define our power, actually it is simply the multiplication of voltage and current. Actually it is the multiplication of voltage and current. But if you are defining it in the phasor form, see what is happening. Suppose you are saying this is the voltage. And suppose the current is lagging this voltage by some angle phi. The voltage is, current is lagging with this voltage with some angle phi. So how you are writing this particular power in terms of real and reactive power? You are writing Vi cos phi. And how you are writing Q as Vi sin phi. So if you define current with respect to the voltage, then there is no problem or no need to take the complex conjugate. But if you are in the absolute frame of reference, this is the relative frame of reference. This is the relative frame of reference. But if you are having the absolute frame of reference, what is the meaning of, sir, absolute frame of reference? Absolute frame of reference means, just see very carefully, it means the reference is like this. And you are defining your voltage, suppose like this. And you are defining your current, suppose like this. So you say this is your voltage, this is your current. Now the angle which this voltage is making with this reference is suppose phi 1 and the current is making this angle phi 2. How you are writing voltage and current? You are writing voltage as voltage magnitude and angle is phi 1. How you are writing the current? Current magnitude, angle phi 2. So if I put S is equal to V into I, what you are getting is magnitude V, magnitude I, angle phi 1 plus phi 2. Now this is the problem. This is wrong. This is wrong. This is the reason we are taking the complex conjugate. Because from here, if I will define the real and reactive power, we need the relative angle between the voltage and the current. We need phi1 minus phi2. To get this difference of the phasor angle, we need the complex conjugate. So everybody just tell me in the comment section. Just tell me in the comment section, are you able to get this? That why we are taking the complex conjugate? I hope we have answered the question. Because if you are in the absolute frame of reference, you need the relative angle between the voltage and current phasor, and for that purpose, complex conjugate is important. I hope it is clear. I hope it is clear. So if you are writing the complex power as voltage multiplied by the complex conjugate of current, this is voltage magnitude angle phi1, and this is current magnitude angle minus phi2, because you have taken the complex conjugate. Now it becomes magnitude V, magnitude I, angle phi1 minus phi2. Now from here, if you calculate the real and reactive power, now you get the right answer. Cos of phi1 minus phi2. Reactive power, magnitude V, magnitude I, sine of phi1 minus phi2. Just tell me in the comment section, are you able to follow this? Now let us answer the second question, that even if we are taking the complex conjugate, why the current is so bechara? Why not voltage? Why this discrimination happening with the current? There is no discrimination. There is a logic. There is a convention behind this. There is a convention behind this. Why complex conjugate of the current? Why complex conjugate of current? Please understand. When we are writing VI complex conjugate is equal to P plus JQ. Now this is the convention, or this is the standard as we are defining the sign convention for the source and the load. If we talk about the source and if we talk about the load, how this is going to be same? How this is going to be same? Because in general, what is the nature of source? To supply power. Source, supply power. What is the nature of load? To absorb power. Yes or no? So if you are writing this equation for the source, and if you are getting P or Q positive, what does it mean? That much real or reactive power is being supplied by the source. Say yes or no. The basic nature of source is to supply power. If you are applying this equation to get the complex power, voltage multiplied by the complex conjugate of current, and you are writing P plus Q, P plus JQ. So if you are getting P or Q, P and Q positive, it means that much real or reactive power is being supplied by the source. And if you are getting the real and reactive power, or any one of them or both of them negative, it means this is the amount of real or reactive power which is absorbed by the source. Which is absorbed by the source. Don't be in this dilemma that source can only supply the power. No, source can also absorb the power. Very simple logic. We'll see how it is going to be. Similarly, for the load, if we are writing this equation for the load, it means if we are getting P or Q as positive, any one of them or both of them, it means that much real or reactive power is being absorbed, because the basic nature of load is to absorb power. So that much power is absorbed. Sir, if you are getting P or Q or both of them negative, it means this is the amount of real or reactive power which is going to be supplied by the load. It means the load can also supply the power. Yes or no? It is supplied by the load. Now let me just prove this point, that even a source can absorb power and even a load can supply the power. Let me just give you some idea. Okay. I hope till now I'm clear. I hope till now I'm clear. Now take the example of an ideal inductor. If you are having one ideal inductor like this, suppose the voltage is V angle 0. The current which is taken by this inductor, I am saying, is IL angle minus phi. Because we know that the inductor is going to draw a lagging current. Lagging current means current is lagging from the voltage. Current is lagging from the voltage. If it is 0 angle, it is minus phi. Say yes or no. I am rewriting this circuit in a different way. I am saying, okay, what I do, I reverse the direction of current and I am going to put a negative sign. Can I do this? Sorry. Let us write it as minus 90 because it is a pure inductor, na? Ideal one. So it is going to be, the current is lagging with the voltage by exactly 90 degrees. I am putting a negative sign and changing the sign of the current. Changing the flow of the current. Can I do it? Yes, I can do it. So it becomes minus of IL angle minus 90. Now let us draw the phasor diagram. This is case 1 and this is case 2. This is case 1 and this is case 2. So let us talk about case 1. Case 1, suppose this is the voltage. Current is lagging the voltage by 90 degree. This is IL angle minus 90 degree. This is 90 degree lag. Is it clear? Now for the case 2, I am going to draw the phasor diagram. For case 2, I am going to draw the phasor diagram. So this is the voltage. This is the voltage. And I have to draw the negative of this current. Negative of this current means you can reverse it by 180 degree. So I am going to write it like this. I am writing minus IL angle minus 90 degree. Now you see, if you closely observe, this current is the current which is lagging this voltage. And this is the current which is leading this voltage. Sir, what does it mean? It means when you are writing for the pure inductor, it means your inductor is absorbing lagging reactive power. Hello? Lagging reactive power. What is the basic nature of inductor? Inductor is a load or source? Inductor is a load. Anything which consumes power is a load. Anything which generates power, we can call it a supply or source. So pure inductor or ideal inductor is going to be a load, and the basic nature of load is to absorb power. So when you are writing like this, it means you are saying the inductor is absorbing the lagging reactive power. But when you say minus of IL angle 90, now this inductor looks like it is supplying the current. It is not absorbing the current. It is not taking the current. It is supplying the current. Supplying the current means it is supplying the leading reactive power. It is supplying the leading reactive power. Everybody just tell me yes or no in the comment section. Are you able to follow this or not? Something really important. Just tell me in the comment section. Are you able to follow this? Good evening, Sham. I will be dealing with the technical subjects, core technical subjects, okay? Maybe like power system and machines like this. Everybody just tell me in the comment section, are you able to follow this? Similarly, you can define for the capacitor also. Similarly, exactly, you can define for the capacitor also. If we talk about the pure capacitor, if we talk about the pure capacitor or ideal capacitor, if it is going to be an ideal capacitor or pure capacitor, suppose something like this. So you can write the voltage angle 0 degree, and this capacitor is going to draw a leading current. Leading current means this is going to be IC angle plus 90 degree. The same circuit you can draw like this. So this is going to be voltage angle 0 degree. And if you reverse the direction of current, you have to put one negative sign. Something like this. So again, in these two cases, you can say that the pure capacitor or the capacitor is going to absorb the leading reactive power or in other way you can say your capacitor is going to supply lagging reactive power. Now first you tell me that are you able to follow me till this, then we are going to proceed to the next topic. This is something really very fundamental and very important. If you understand this, then further topics are going to be easy for you. Definitely we'll come for engineering services also. We'll launch courses related to engineering services also. Already that is in pipeline. But we are not in a hurry. We are not in a hurry. Okay, we want to make a very strong base, and for that purpose we are starting little slow, but we want to have a very strong base. So last year we started with the GATE electronics batch. This time we are starting with electrical also. So slowly we are starting. Definitely it is in pipeline, and if we get the right time, definitely we'll start with engineering services also. Okay. Is it clear for everybody? Now you see, the convention is, suppose one student come to me and he's asking, sir, give me 10 rupees, I want to eat chocolate. Now I'm a very good person. I will give 10 rupees to that student. But that student is very notorious. When he's going back to his team or his group, he's saying, Ashutosh sir has not given me 10 rupees. I have given Ashutosh sir minus 10 rupees. Actually, what he's saying is right. Actually, what he's saying is right. I have given 10 rupees to that student, or that student has given me minus 10 rupees. Both are the same thing. But for a convention, so that there is no confusion, we generally go with two standard conventions. What are those two standard conventions? Those two standard conventions is, when we talk about the capacitor, we generally say that it supply lagging reactive power. It supply lagging reactive power. And when we talk about the inductor, we generally say it absorbs lagging reactive power. Our reference is lagging reactive power in general. But if you get a question in GATE examination, if they want to confuse you, then they can trap you in this. But you are smart, you can understand that how to deal with these type of issues. Okay, Ashish, so I hope you have studied ethics with me. That was a great experience for me also to connect with you guys for that very loving subject. Anyways, now let's proceed. So let me just first talk about the single phase power. Let me just first talk about the single phase power. So single phase power, you can say, suppose we have a source like this. Okay. We have a source like this, and suppose this is the load. This is the source and this is the load. Okay. Now source, suppose we are defining as root 2V sine omega t. This is the AC source, time dependent source, root 2V sine omega t. And the current, this is going to be, suppose, the RL load. So if it is the RL load, we can define the current or the instantaneous current as root 2I sine omega t minus phi. Because we are saying that this is the inductive circuit, okay, RL circuit. So the current is lagging with the voltage. How much? We don't know. But when you are writing the voltage and the current like this, it means these voltage and current, these are the RMS values. You understand what are RMS values? RMS value means effective value of the alternating quantity. Everybody just tell me in the comment section, do you understand what is RMS value? Root mean square. What is the physical or practical understanding of it? It is the effective value of that particular physical quantity. Okay. So V and I are written in the RMS form, because if you see, if you are writing in the sinusoidal form, suppose you are writing, so this is the peak value. This is the peak value. So if you have to write the RMS value, or in general, if I simply write V, it is going to be the peak value divided by under root 2. In other way, if you have to write the peak value, you can write it root 2 times the RMS value. So from that reference, I have written the instantaneous voltage and the current in the circuit like this. Now, if using these voltage and current, I want to write the instantaneous power. Instantaneous power. How I'm going to write the instantaneous power? I'm going to write the instantaneous power simply as the multiplication of instantaneous voltage and instantaneous current. Say yes or no. Are say yes or no. Instantaneous power means at this moment, what is the voltage? Instantaneous current means at this instant, what is the current? Simply put the expression for Vt and It, it is root 2V sine omega t multiplied by root 2I sine omega t minus phi. Current we are showing as lagging with reference to the voltage. Now if you solve this, what you are getting, I don't want to go into the derivation part because that is not important for GATE examination. You will get Vi cos phi 1 minus cos 2 omega t minus Vi sin phi sin 2 omega t. If you do some trigonometry, you will get this expression. Okay. Sir, what is this? Can you tell me, sir, what is this? This is real power. We are defining the real power as Vi cos phi. Sir, what is this? This we are defining as the reactive power Q, that is Vi sin phi. So can I write this expression again? Instantaneous power in this circuit is going to be P 1 minus cos 2 omega t, okay, minus Q sin 2 omega t. This is the expression to write the instantaneous power in any single phase circuit. And I am repeating, it is the instantaneous power in any single phase circuit. Now there are two important observations which can be asked in your examination. Now I want the average power of this instantaneous power. Now you know that for any sinusoidal term means sin omega t, cos omega t. Time dependent sin omega t is time dependent cos omega t. If you take the average, the sinusoidal curve, sin omega t, or cos omega t, for a complete cycle, the average is 0. For a complete cycle, the average is 0. It means this term cos 2 omega t is not going to give us anything if we take the average. This term also sin 2 omega t is also not going to give us anything if we take the average. So what is the remaining? The remaining one is this P. So the average of this instantaneous power is simply P. Now I want to tell you the real name of this P. The real name of this P. This P is, which we generally call as the real power, is actually the average instantaneous power. Average instantaneous power. Say yes or no in the comment section. This is the average instantaneous power which is equal to the real power, which is equal to the real power, which you simply write as P is equal to VI cos phi. And it is because of this reason we are saying that we can get the useful work only by the real power, not with the reactive power. Is it clear? Say yes or no in the comment section. Is it clear? अरे चमका कि नहीं चमका बाबू? Tell me yes or no. 3-4 डिग्री टेम्परेचर में भी देखो पसीने आ रहे हैं. I am sweating in this low temperature. So can you just tell me yes or no in the comment section? Now understand one very interesting fact. If you see this particular equation, 1 minus cos omega t, cos 2 omega t minus q sin 2 omega t. Okay? Don't get confused with this negative sign. People get confused out of this negative sign. Sir, why we are getting this? Is it mean that reactive power is negative? No, 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 no. It is nothing like that. It is simply an expression. It is simply an expression. No, no, I'm just joking. I'm just joking, Ashish. Okay, focus, focus. You are getting this negative sign only because of the expression. There is no significance of this negative sign. I will show you the graph. I will show you the graph. Let me just show you the graph. Can you see this graph? Is it visible to all of you? Can you see this graph? If you see this one, okay, this is the axis. This is the axis omega t, okay, and this one is the voltage. This is the voltage. It is starting from here. The other one is, the dark one is current. This is the current. And if you see, current is starting after a gap of angle phi. So current is starting after. That is why we are saying current is lagging. Something lagging means starting after. Okay. So if we say current is lagging with respect to voltage, it means current is starting after some time when the voltage has already started. So voltage has started here at this time instant, but the current has started after a gap phi. Is it clear? Now we are saying the instantaneous power is the product of the instantaneous voltage and current. So at every point you have to multiply voltage and current, and you can draw the instantaneous power curve. So this dotted curve, if you see, this dotted curve, I hope you are able to see, it is the curve for instantaneous power. Now if you are able to see this, you will be able to see its average one. You may get a question in the GATE examination on this graph. The average one, I'm just showing it with the red. Yes. Red color. Can you see this dotted one? This is actually VI cos phi, and which is the average of that instantaneous power, which is the average of this instantaneous power. I hope it is clear. Now, why you are getting the negative sign there? Just see this graph. This instantaneous power is being divided into two parts. This is the instantaneous power. Okay, it is being divided into two parts. This is the first part, and this first part is nothing but this one, P1 minus cos 2 omega t, and this second one, which was a sinusoidal, Q cos 2 omega t, it is a sinusoidal one. So this is the sinusoidal one. Okay. So this second one is Q sine 2 omega t. Now there is a reason why I'm explaining you this particular diagram. So you can see that graph number 1 and graph number 2, they are superimposed so that you get this instantaneous power. So don't get confused with this negative sign. It's just a part of your expression. It's just a part of your expression. Is it clear? Is it clear? Now you see, when you write this single phase power and you are writing P is equal to VI cos phi, and you are writing Q as VI sin phi. Now when you say your current lagging the voltage, when you say current lagging with the voltage, it means you are writing V is equal to, sorry, I is equal, or we can write, if you're writing V is equal to root 2V sine omega t, then you are writing I as root 2I sine omega t minus phi. Simple. Okay. This is instantaneous voltage, this is instantaneous current. So when you say current lagging the voltage, it means this phi is positive here, this phi is positive here. But if you say current leading the voltage, if you say current leading the voltage, if the current is going to lead the voltage, in that case you will be writing, sir, the instantaneous voltage as root 2V sine omega t and current IT as root 2I sine omega t plus phi, because current is leading the voltage. It means when you are going from the lagging case to the leading case, you are putting minus phi in place of phi. Minus phi in place of phi. So if you put minus phi in place of phi, there will be no change because it is cos phi. Cos theta and cos minus theta is same. But if you change phi to minus phi, this Q is going to change the sign. This Q is going to change the sign. It means, what I want to tell you, that it will save a lot of your time in the real examination, GATE examination. If you are having a lagging case, then how you are writing the instantaneous power? It is P1 minus cos 2 omega t minus Q sine 2 omega t. But if it is a leading current case, then in that case, it will become P1 minus cos 2 omega t plus Q sine 2 omega t. Just tell me yes or no in the comment section. Are you getting this? This is the only difference you get in this expression, in this equation, when you talk about the lagging case or the leading case. Tell me yes or no in the comment section. Are you able to follow this? Only one candidate is responding, Ashish Raj. So we need only one rank. Rank 1 is going to be 1 only. There cannot be 2 people on the same rank. So we have got 2 conclusions out of this equation, that number 1, the average of the instantaneous power is nothing but the real power. Second one, the power is going to oscillate at double the frequency. The power is going to oscillate 2 omega. Voltage and current were oscillating at omega, and power, whether it is real power or reactive power, you can say, they are oscillating at a frequency twice the voltage and current. I hope it is clear for everybody. Is it clear? Now let us talk about 3-phase power. Now let us talk about three-phase power. Three-phase power. Now what do we mean when we say three-phase power? Please understand this. Very important term, balanced. If the term balanced is there, it means everything is okay. If the term balanced is not there, then you cannot be 100% sure. For what? If we are saying our three-phase power system is a balanced system, it means if we talk about the voltages or if we talk about the currents, whether we talk about the line voltages or phase voltages, or we talk about the line currents or the phase currents, they are going to differ by an angle of 120 degree and their magnitudes are going to be same. This is what we understand when we say balanced system. Say yes or no. Whether it is A phase, B phase or C phase, their voltage magnitudes are going to be same, but in terms of phasor, the phasor difference between two consecutive phasor is going to be 120 degree if it is a balanced one. Same is the case for the current also. Same is the case for the current also, yes or no? So if it is a balanced three-phase system, then we can write, suppose we are writing the A phase voltage. Suppose we are writing the A phase voltage. ओम प्रकाश जी इंपॉर्टेंट टॉपिक बता दीजिए पावर सिस्टम के लिए. बेटा मैंने I have already explained the important topics for power system in the starting part of this video. Okay, so if you just want the important topics, you can just scroll and see the important topics. Already in the starting part I have discussed. So suppose we are writing the three-phase power. So first we are writing the power voltage and current for the A phase. Okay, and the phase sequence is ABC. Phase sequence is also important. If phase sequence changes, a lot of things are going to change. Phase sequence is ABC. So you are writing the A phase voltage as root 2V sine omega t. Say yes or no. And you are writing the A phase current as root 2I sine omega t minus phi. Why minus phi? We are assuming that it is a lagging case, so the current is lagging the voltage. So for A phase I have written root 2V sine omega t, and for A phase current I have written root 2I sine omega t minus phi. If I want to write the B phase voltage, instantaneous voltage, I can directly write, if it is a balanced case, root 2V sine omega t, sir, minus 120 degree. Minus 120 degree. Why minus 120 degree? I will tell you. Okay. If we are writing C phase, so it is going to be root 2V sine omega t plus 120 degree. Similarly, for the currents also we can write the B phase current, you can write root 2I sine omega t minus 120 degree minus phi. And the C phase current you are writing as root 2I sine omega t plus 120 degree minus phi. Say yes or no. We are writing the voltage and current for each phases. Why we are writing so? Suppose you have a star connection. Suppose you have a star connection. Okay. Suppose this is VA, this is VB, and this is VC. What is the phase difference between them? 120 degree, 120 degree, and 120 degree. So if you are saying VA is root 2V sine omega t, it means for writing this C, you need to add 120 degree in omega t. So it is root 2V sine omega t plus 120 degree minus phi. But if you see B, instead of adding 120 degree, you have to subtract, or you have to write minus 120 degree. So you are writing root 2V sine omega t minus 120 degree. Say yes or no. Similarly, for the currents also you can write. Third harmonic component you can discuss when you talk about machines. When you talk about machines, you will get the idea about the third harmonic component, okay? There it is going to be important. Is it clear? Anyways, so I hope you are getting this. Now, suppose if we write the total three-phase power out of this. Suppose if we write the total three-phase power, how we are writing the total three-phase power? The total three-phase power we are writing as the power in A phase, the power in B phase, and just keep on adding the power in C phase. Instantaneous powers in the A phase or the B phase or the C phase, just add them up and you will get the three-phase instantaneous power. Now, if you add them up, what you are getting is 3 times Vi cos phi. I'm not going to the derivation part, that will save our time, and that is actually not required here also. That is also not required. So you're writing 3 times Vi cos phi, which is nothing but 3p. Now there is something really very surprising. If you can observe that if you see the instantaneous power in case of a three-phase system or three-phase circuit, you are getting it as constant. You are getting it as constant. There is no time term. V and I are the RMS values. And let me tell you, when you write the voltage and currents like this, this V and I, what is V and I? Very, very important part. This V and I are the per phase RMS values. These are the per phase RMS values. Be very specific in this. Because when you are writing the voltage, you are writing root 2 V for A phase. So this root 2 V is the peak value of the phase voltage. Are you getting this? So this V and I is going to be the per phase RMS values. This is going to be the per phase RMS values. Is it clear, everybody? Is it clear? It is very, very important when we are writing it as 3 Vi cos phi, we are writing it 3 times P, then it is important to understand that what you are writing P as Vi cos phi, this voltage and current, these are the per phase RMS values. Per phase RMS values. Then only you can apply this formula. So one surprise you have got, that when you calculate the instantaneous power in a three-phase circuit, there is no reactive power term. Ha 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 ha. He 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 he. There is no reactive power term. Where the reactive power has gone? Reactive power is in the system, because you are saying current is lagging with the voltage. So what has happened with the current, with the reactive power? Because when I'm calculating the instantaneous power means at this moment. So at any moment from 0 to infinity, if you traverse the time, you are only getting the real power 3 times the per phase real power. 3 times the per phase real power you are getting. So where have gone the reactive power? Can you tell me yes or no? See, the reactive power has not gone anywhere. Reactive power is there in the system. To answer this question, I will give you one example. Suppose I take a very simple circuit. Now this is one inductor and this is one capacitor, and these are the ideal one. Ideal means pure. There is no resistance. There is no resistive element in this circuit. So the energy which can be absorbed by this inductor is going to be half Li square. And the energy which can be absorbed in this capacitor is half Cv square. Now, if you want to know at any moment what is happening with the reactive power is actually oscillating from this inductor to the capacitor. It cannot be consumed. Are you getting this? So the reactive power is there in the system. But when you calculate the instantaneous power in a three-phase system or three-phase circuit, you are getting it constant all the time. You are getting it constant all the time. So even if you don't see it when you calculate the instantaneous power, but still the reactive power is there in the system. Still it is there and you can find it. You can find it, yes or no? So what is going to be the reactive power? As you are defining P as Vi cos phi, which is the per phase real power, in the same way you can write Q as Vi sin phi, which is the per phase reactive power. And if you want to write total three-phase power, whether it is real power or reactive power, just multiply it 3 times, because you are writing in terms of per phase. For 3 phase, you have to multiply it by 3. Good evening, Nutan Kumar. How are you? Welcome to the session. Joining so late. Are you getting this? Just 1 hour you want to break? Please wait, please wait, wait. Okay? Please wait. Stop not till the goal is reached. Arise, awake, and stop not till the goal is reached. Swami Vivekananda. Okay? You can just go have some water. Okay? Don't eat your dinner, otherwise you will go to sleep. Just have a little bit of water, maybe something to eat. Okay? We have to continue because a lot of things we have to discuss. So is it clear? So are you getting, even if you are not getting the component of reactive power in the instantaneous power, it does not mean that there is no reactive power in the system. Reactive power is there in the system. But what you are getting as the instantaneous power in a three-phase circuit or three-phase system is a constant one, and it is equal to 3 times the per phase real power. I hope it is clear. So we have just discussed about the three-phase, a single phase and three-phase real and reactive power. I hope it is clear for you, and it is very important also at the same time. Now let me just talk about the star delta connection. Very simple, very important. Star delta connection. If we talk about three-phase systems, generally in your syllabus or at your level, they are going to ask whether it is a star connection or delta connection. So let me just discuss 2 simple cases and then we'll proceed for the next topics. So if we talk about the star connection, sir, if we talk about the star connection, in machines you are going to read it in a very large way, so I'm not going too much into this. So if you are having a star connection, it is something like this. And because we are treating it as a load, so suppose this is how it is getting current. Now if you see the voltage, suppose this is A phase, this is B phase, this is C phase, and this is the neutral or the reference you can say. So this is VAN. Similarly, you can find VBN and VCN. So if I write VAN, VBN or VCN, these are the phase voltages. These are the phase voltages. But suppose I want to know the voltage between A and B phase. So that is VAB. Similarly, you can write the voltage between B and C and A. So you can write VAB. VBC, VCA. So these are going to be line voltages. These are going to be line voltages. These are going to be line voltages. But if you see the currents, suppose you are saying, sir, this is IA, IB, and this is IC. It means the currents in the line or the line currents are IA, IB, IC. Now the same current is going to enter into the phase. The same current is going to enter into the phase. So you see, in case of a star, line current and phase current, they are exactly same. Current is not going to change when we talk about the star connection, whether it is line current or phase current. But in terms of voltage, there is a difference. We define these phase voltages as V phase and these line voltages as V line. So you can see, in terms of the magnitude, if we write in terms of the magnitude, so the magnitude of the line voltage for a star connection is going to be √3 times the magnitude of the phase voltage. We all know this. We all know this. Okay, but we have to talk about it. But if I have to write VL, so we can write it √3 times magnitude V phase, and angle is going to be how much? Or let us write like this: V phase and angle is going to be plus 30 degree. Angle is going to be plus 30 degree. It means what? Very important conclusion, very frequently used in solving a lot of questions, that in case of a star connection, the line voltage leads the phase voltage by 30 degree. Very, very important conclusion. If you don't know, then you can just note it down. If you know this, then it's okay. Okay. So if you have the expression for the phase voltage, can you directly write the exact expression for the line voltage with this equation? Yes. Currents are not going to change when it is a star connection, whether it is line current or phase current. Now let us talk about the delta connection. If you talk about the delta connection, again, let me just something like this. So this is going to be A, B, C. Okay. Again, because we are treating it as a load, so currents are coming like this. So this is going to be IA, this is going to be IB, this is going to be IC. Now these IA, IB, IC, these are the line currents. This IA, IB, IC, these are the line currents in the line. But if you see the phase A to B, you are getting the current IAB, B to C, you are getting the current IBC, and C to A, you are getting the current ICA. It means if you write the phase currents, these are going to be IAB, IBC, ICA, and these are the phase currents. These are the phase currents. But if you talk about the voltage, now you see, if you talk about the voltage, the line voltage and phase voltage, they are going to be exactly same. Whether you talk about the line voltage or phase voltage, because phase is going to be same in terms of the voltage if it is a delta connection. Currents are going to be different. How you are writing the currents? Now see very carefully. If I am writing the magnitude of line current, again it is √3 times the magnitude of the phase current. Magnitude of the phase current. But if I want to relate in terms of the phase, so see, phase current I am writing line current divided by under root 3 angle plus 30 degree. It means in case of delta connection, the phase current is going to lead the line current with 30 degree, or you can say vice versa, or you can say the line current lags the phase current by 30 degree. That is what you can say. So just note it down if you don't know, that in case of delta connection, the phase current lead the line current by 30 degree. Is it clear, everybody? ये वाला part आपने network में पढ़ा होगा. Okay, you have seen this part in the networks. Okay, see, these subjects are overlapping, subjects are interrelated, but how you deal with that particular topic, that is important for any specific subject as per the requirement of the subject. If you understand that link, it means you have decoded GATE. Because GATE is all about linking these subjects. If you can relate networks to power system, if you can relate networks to electrical machines, if you can relate control system to other parts of your subject, it means you have done it. It means this is the time you have to do little bit of hard work and you will get your goal. Okay. So we have discussed about the star and delta connection also. I'm not going for the phasor, that will take a lot of time and we have very limited time. Okay. So this is about the very basic of single phase and three phase power. Now let me just proceed a little bit. So if you talk the very structure of our power system, as you can see in this diagram, so we have generators, transformers, transmission lines, again transformers, and we have distribution network. Finally, we are going towards the load. So there are different voltage levels. You can see that we are having transmission level voltages, then sub-transmission level voltages, then primary and secondary distribution. So this is the whole structure of your power system. This is the whole structure of your. कुलदीप मित्तल is saying, sir, एक request है, क्या आप हिंदी में पढ़ा सकते हैं? मैं बेटा तुम्हें किसी भी लैंग्वेज में पढ़ा सकता हूँ. I am a polyglot. Polyglot, you know? Polyglot. देखो मैंने तुम्हारी इंग्लिश का एक vocabulary बढ़ा दिया. Polyglot. Polyglot is a person who can speak more than one language. So I can speak Hindi, English, a little bit of Sanskrit also. ठीक है? हमारे टाइम पे यही होती थी. हमारे टाइम पे सब जर्मन स्पेनिश इतना ज़्यादा नहीं था, हम जिस स्कूल से पढ़े. But the idea is we want to serve the larger audience. We want to service the larger audience. Okay? So if I'm just restricting myself to Hindi, or if I'm too much going into Hindi, so many candidates will not be able to connect. But I'm using very simple English. If you can understand a child's abba dabba chabba, then you can understand my English also. That is so simple. I hope, and I'm not just running like a machine. I'm talking in a very proper way so that you can understand my English. See, if you want to learn something a little bit, you have to sacrifice. Everything does not come to your doorstep. Okay? Anyways, if you have a doubt, you can, any technical doubt if you have, you ask me, sir, please repeat in Hindi. I will definitely repeat. But the basic mode of conversation is going to be English because we want to service a largest number of students. That is the case. Okay? That is why I'm using English. Okay? So I was talking about the very structure of our power system. Okay? Now, the moment you see this diagram, one thing comes into your mind: single line diagram. Yes, single line diagram. You are getting so many questions also, you are getting this type of diagram. So we are using the single line diagram basically to use unique symbols for different components of our power system, and we want to represent our complex power system in the easy way. Yes or no? Like your computers, power system is also one of the most complex man-made system on this planet. If you don't believe it, just go outside and see your electric pole, you will understand how complex it is. That is also a part of power system. So just to understand our system, just to understand different components in our system or analyze them or make them better, we have single line diagram. Single line diagram is nothing but we are using unique symbols. The key idea is unique symbols. Sir, what is the meaning of unique symbols? The meaning of unique symbols is that we are using this circle for the generator. If you write M inside, it becomes motor or the load. This symbol for the transformer. Are you getting this? So different symbols we are using to represent our system. Now if you have this type of system, can you analyze it? Say yes or no? No, sir. Because we can only analyze our power system if we have the circuit. Because we are electrical. We only talk about voltage and current, KCL, KVL. There is no third law. In mechanical, we have lot of laws. In civil, we have lot of laws. In computer science, we have lot of laws. But electrical, we have only two laws. Come what may. KCL and KVL. There is no third law. So we want a circuit which we can analyze, and that is how we can make our system better. For that purpose, so this is the single line diagram. Can you see? Single line diagram. Everybody just see this. This is a generator. Then we have a circuit breaker, then transformer. Then we have two parallel lines, line 1, line 2. Again a transformer, and we have two loads, M1, M2, M1, M2 in terms of load. So just representing our system or power system in a pictorial form, we are using the single line diagram. But we cannot analyze it by this diagram. We have to draw the reactance diagram. So what we are doing, we are replacing each component with its impedance or the other parameters. If it is a generator, then voltage also. Yes or no? So if you see, this is going to be the impedance diagram. This is the generator, the internal reactance of the generator, Xg, then the reactance of the transformer, Xt1, then the reactance of the transmission line 1, reactance of the transmission line 2 in parallel, again a transformer, and we have two loads. Loads are going to have back EMF, because if it is a motor, so we are writing EM1, EM2, and the reactances are XM1 and XM2. This is what we call as reactance diagram. This is what we call as reactance diagram. And this diagram we require to analyze or understand our system. Because this is something we can apply KCL, KVL. Say yes or no. Say yes or no, Nutan Kumar. Are you getting this? Now, there is a problem. Sir, what is the problem? Before we proceed, there is one more tool you have to understand that we call as per unit system. That we call as per unit system. Sir, what is per unit system? Please understand. Suppose I am giving you a particular circuit. Suppose a very simple power system, a generator, okay? Two parallel lines, now having individual transformers. This is line 1, another transformer, line 2, another transformer, okay? And suppose some load is, a static load is connected here. Sir, what is happening here? Please see. Now this is a generator. Listen, this is a generator. Suppose this generator is having 11 kilovolt. Suppose you are generating the power at 11 kilovolt. These transformers are suppose 11/66 kV. 11/66 kV. These transformers suppose 66/11 kV or 66/11 kV. And suppose this static load is having 10 kilovolt. I'm just writing the voltage. I'm just writing the voltage. Because in our power system, this is one of the simplest power system, the radial form of power system. Okay, we have ring connections also. Yes or no? Loop connections also. And we have very complex interconnected system. But for just simple understanding, we are having a simple example of a power system. Now you see at generator side, the voltage is 11 kilovolt. The line side, the voltage is 66 kilovolt. And again at the load side, the voltage is 10 kilovolt. It means if you are going to write the KVL equations, you please understand how complex it is going to be. How complex it is going to be. You have to write, suppose one equation for this part because this is 11 kilovolt. This equation, so many equations that it is going to be very complex. Just understand if it is a three-phase system, how complex it is going to be. Just understand. And this problem is happening simply because of the transformer. The transformer is having some discontinuity. We'll understand what type of discontinuity. And that is the discontinuity of the voltage. Voltage is different at this part, voltage is different at this part. We want to remove this discontinuity. How to remove? For that purpose, we want a system which can simplify our system and we can do an easy analysis. For that purpose, we are having per unit systems. Per unit system, simply what we are doing, we are actually normalizing our system. We are normalizing our system in terms of voltage magnitude. But if you see in our power system, either you can have voltage, you can have current, you can have power, or you can have impedance. These are the four basic parameters. If out of these four parameters, if you know any two parameters, rest two parameters you can easily solve. Yes or no? So generally what is happening, whether it is voltage, current, power, or the impedance, what we are doing, we are choosing base. What is base? Suppose you have 10 marks in one examination, another candidate is having 8 marks, another candidate is having 7 marks, another candidate is having 15 marks. I want to compare your performance. So I need a benchmark. I need a base on which I can compare your performances. Similarly, in our system, we need a benchmark, we need a reference. That reference we are defining as base. So it may be a voltage, it may be a current, it may be impedance, it may be power. So we are defining base as the reference. And if you want, for any quantity, any physical quantity, if you want to write the per unit value, it is simply actual value divided by base value. Actual value divided by base value in 1 unit and base value in the same unit. This is the basic idea. So suppose I am writing per unit voltage. What I need? Actual value of voltage and base voltage. Suppose I am writing per unit power. So I need the actual power and the base power. See, yes or no? Suppose I am writing the current in terms of per unit. Actual current divided by base current. If I am writing the impedance per unit, I simply need the actual value of the impedance divided by the base value of the impedance. Now, if you see most of the problems, whether you go for machines or the power system, generally our electrical equipments are being rated in terms of their power and voltage. Because the current is going to be decided by the load. In general, a standard way of writing the rating of any equipment, electrical equipment, is writing the power and the voltage. From that reference, you can say, generally we choose power and the voltage base. Now, if you have power and voltage base, you can find the base for the rest of the two quantities. Suppose you want to find the base current. So if you have base power and base voltage, so this is simply base power divided by voltage base. If it is a single phase circuit. Now, if it is a three-phase circuit, it is simply going to be power divided by under root 3 voltage base if it is a three-phase circuit. Say yes or no. Now, if you talk about the impedance, impedance you are defining as the square of the voltage divided by power base. Square of the voltage divided by the power base. Is it clear? Now suppose using these bases, I am writing the per unit value of the impedance. So it is going to be the actual value of the impedance divided by the base. Now what is base? It is Z divided by square of the base voltage into base power. Now you see, suppose you have two different systems. Okay. Suppose you have two different systems, base 1 system and you have base 2 system. Base 1 system and base 2 system. So base 1 system, suppose you are having SB1 and VB1 as the power and the voltage base, SB2 and VB2 as the power and voltage base for different systems. Now suppose the per unit value of the impedance is Z per unit 1 here and it is Z per unit 2 here. How you are going to relate it? Now whether it is base 1 or whether it is base 2, your actual value of impedance is not changing. Actual value of impedance is not changing. It means this is a constant. So sir, what is changing? Base power and base voltage is changing for two different base systems. Sir, can I write that the per unit value of the impedance is proportional to SB upon VB square? Can I write like this? Yes. Using this equation, you can write Z per unit new is equal to Z per unit old multiplied by MVA base new upon MVA base old multiplied by kilovolt base old divided by kilovolt base new, and this is the square. This is the general expression for transforming a given per unit in a given base system to a new base if you want to find the per unit value of the impedance. Is it clear for everybody? Say yes or no. Ashish, we talk about them also. We'll talk about them also. Don't worry. We'll talk about real reactive power. Everything we'll discuss. Okay, don't worry. Don't be in a hurry. Have a bit of patience. We'll discuss each and everything. So I hope it is clear for you. Now this is the very basic part. Okay. Now Ashish is asking about, suppose we talk about the complex power. Please see very carefully. This is something from where a lot of people are doing the mistake. Suppose you talk about the complex power. So complex power you are defining S as P plus JQ. Suppose you are defining SB as the base or the base power. How you are defining the per unit complex power? Actual power divided by the base. What is S? P plus JQ. This is S base. So per unit complex power you are defining as P upon SB plus J Q upon SB. Now please understand, this is what we are saying P per unit. This is what we are saying Q per unit. So this SB is the base complex power, volt ampere. You understand? Complex power is volt ampere. Real power is watt. Reactive power is volt ampere reactive. I hope you know this. Similarly, when you write for the impedance, impedance is also a complex quantity. How you are writing impedance? Z. This is R plus JX. Suppose if you are writing in this way. And ZB is the base impedance. ZB is the base. How you are writing the per unit value? The per unit value is going to be actual value divided by the base value. Z is R plus Jx divided by Z base. So it becomes R upon Z base plus Jx upon Z base. Now, my dear friend, this is what we call as per unit resistance and per unit reactance. This is what we call as per unit impedance. Be very clear in this, don't do the mistake. Are you getting this? Now let us understand our very fundamental problem, how our per unit system is solving this problem. What was the problem? The problem was the discontinuity because of the transformer. The discontinuity because of the transformer. Say yes or no. So let us talk about the transformer. Now please understand, when you say transformer, so basically there are two circuits which are isolated but magnetically coupled. Isolated but magnetically coupled. Now if you see, suppose you are saying number of turns N1, number of turns N2. Suppose here the voltage is V1, the current is I1. Here the voltage is V2, the current is I2. Now just for the simplicity, I'm choosing for the two circuits, this circuit and this circuit. We can say primary also, we can say secondary also, we can say high voltage also, we can say low voltage also. Depends upon the way we are talking about it. I'm choosing for the primary circuit V1B and I1B as the voltage and the current base. Now for the secondary circuit, I am choosing V2B and I2B as the voltage and the current base. If we have two quantities fixed in terms of bases, rest two quantities base we can easily find. If we know voltage and current, we can find the base of power also, we can find the base of impedance also. Yes or no? No problem with that. Now let us first talk about some relations. So we are saying K is equal to N2 upon N1. This is the turns ratio. Turns ratio of the transformer simply. Now you see, if I write V2 upon V1, it becomes equal to I1 upon I2. And this is equal to N2 upon N1. And this is equal to K. Now this equation you can only write if one condition is fulfilled. That is why per unit system you can apply only if one condition is fulfilled. What is that condition? Sir, what is that condition? Magnetizing branch of the transformer equivalent circuit. Transformer equivalent circuit is neglected. Sir, we don't understand what you are saying. Please understand this. Please understand this. When you are writing the equivalent circuit of the transformer, suppose you are writing like this. Suppose some load is connected there, okay? Suppose this is the equivalent circuit of the transformer. Why I am putting this condition? Suppose this voltage I am saying is V1. So this current is going to be I1. This current is I2 dash and this current is I naught. This current is I naught. And this is current I2. This is current I2. Suppose this is N1, this is N2. Sir, what is I2? What is I2 dash? When you transform this current or refer this secondary current from secondary circuit to the primary circuit. Are you getting this? So this is going to be, I2 dash is going to be what? It is N2 I2 upon N1. Okay. N2 I2 upon N1. You are referring the secondary current to the primary side. I hope you know this. If you don't know this, don't worry. When you read machines, when you read transformer, you will understand. Now, what is the problem? You are writing this. Are you getting this? You are writing this relation not for I1. It is I2 dash. And sir, what is I1? I1 is I2 dash plus I0. It means the shunt magnetizing branch current, or you can say the no load current or open circuit current, you can say. So even if there is no load connected, at least some current is going in the shunt branch. But when you connect the load, there is additional burden is put on the source. So more current is taken. What is that more current? That more current is I2 dash. Now, when you are writing N1 I1 is equal to N2 I2, this is only possible when this is 0. Because I1 is I2 dash. I hope you are getting this. Are you getting this or not? Tell me yes or no. If you don't know this, all this, don't worry, leave it. When you read machine, you will get it. Are you getting this or not? Why I'm putting this condition? Because I'm using this relation. N1 I1 is equal to N2 I2. Actually, N1 I1 is not equal to N2 I2 because there is I0 component. So this relation can only be used if you can neglect the shunt magnetizing branch current. Is it clear? Say yes or no in the comment section. Say yes or no in the comment section. So if I can use this relation, then everything is okay in my life. Now you see. I hope it is clear. Now you see. Suppose I talk about the voltage discontinuity. Sir, I am writing the per unit voltage primary side. It is actual voltage at the primary side divided by the base voltage. Sir, I am writing the secondary side per unit voltage. Actual secondary side voltage divided by the secondary side voltage base. Very simple. Sir, you know, if you write V2B upon V1B, this will be equal to N2 upon N1 because of the very transformer turns ratio. Yes or no? V2 base and V1 base can also be connected like this. So this is nothing but equal to K. So if I write V2 per unit, what you can write as V2? V2 you can write as K times V1. N2 upon N1 we are writing as K, so it is K times V1. So it is K times V1 means what? V2 you can write as K times V1. Sir, what you can write as V2 base? V2 base you can write as K times V1 base. So K times V1 base. So K is cancelled. You are simply getting V1 upon V1 base. That is nothing but V1 per unit. It means if you are dealing in per unit, the voltage discontinuity of the transformer is gone. Hello? Are you getting this? Say yes or no in the comment section. Voltage discontinuity gone. Sir, what about the current discontinuity? I am writing the per unit value of the current in the primary side. So actual value of current at the primary side divided by the base current at the primary side. The per unit value of the current at the secondary side is equal to the actual value of the current at the secondary side divided by the base value of the current at the secondary side. Now, sir, how I am writing I2 per unit? See very carefully. If you are saying I2 base upon I1 base, this is again N1 upon N2. Yes or no? So what you can write in terms of I2? You can write I1 upon K. See this relation. What you can write as I2? I2 is I1 upon K. So I'm writing I2 as I1 upon K. Sir, what is I2 base? I2 base also you can write as I1 upon K. I1 base upon K. It means you can write I2 per unit as I1 upon I1 base. It means I1 per unit. So current discontinuity is also gone. Current discontinuity is also gone. It means if you are using per unit system for transformer, you don't need to worry about the current discontinuity. Whether it is primary side or the secondary side, the per unit current is going to be same. Current problem is also solved. Sir, what about the impedance? Okay. Now you see, if you are writing the impedance, suppose I write the base impedance at the primary side, it is going to be the base voltage divided by the base current. Yes or no? I am writing the base value of the impedance at the secondary side. This is the base value of the voltage at the secondary side divided by the base value of the current at the secondary side. Say yes or no. Now you see, in this equation, can I write the base value of the voltage at the secondary side as K times base value of the voltage at the primary side? Yes. Base value of the current at the secondary side you can write as base value of the current at the primary side divided by K. So it becomes what? It becomes K square V1 base upon I1 base. That is nothing but K square Z1 base. It means base impedance, two sides you can relate as K square Z1 base. Important relation. Important relation. Is it clear? Say yes or no. Okay. Now you see, now. I want to write the per unit value of the impedance at the primary side. So what I need actual value of the impedance at the primary side divided by the base value of the impedance. What is actual value of the impedance at the primary side? Primary impedance plus secondary impedance referred to the primary. So it is N1 upon N2 square. So I can write it as Z1 plus Z2 upon K square, because N1 upon N2 is 1 upon K. Say yes or no. Do you know how to write the effective impedance at the primary side? Primary impedance plus secondary impedance refer to the primary side. How to refer? Suppose you are referring Z2 from secondary to primary. So Z2 divided by from where you are going to where you are going. Divided by from where you are going multiplied by to where you are going. So Z2 divided by N2 multiplied by N1, take the square of the turns ratio. Similarly, if I write the per unit value of the impedance at the secondary side, it is the actual value of the impedance at the secondary side and the base impedance at the secondary side. Now what is ZO2? ZO2 is the total impedance referred to the secondary side. So it is equal to the secondary side impedance plus primary side impedance divided by N1 multiplied by N2, take the square. So this is nothing but Z02 is Z2 plus K square Z1. If you take K square common, it becomes Z1 plus Z2 upon K square. Sir, what is Z1 plus Z2 upon K square? Z1 plus Z2 upon K square is Z01. Sir, can I write Z02 is equal to K square Z01? Say yes. It means the effective impedance you have related at the primary side and the secondary side. Base impedance you have related primary side and the secondary side. So can I relate the per unit impedance? Yes. Sir, what is secondary per unit impedance? Secondary actual impedance, secondary base impedance. Secondary actual impedance is K square primary actual impedance. What is secondary base impedance? K square times primary base impedance. It means Z2 per unit you can write as Z01 divided by Z1 base, which is nothing but Z1 per unit. It simply means Z1 per unit is equal to Z2 per unit. It simply means that if you are working in the per unit system, the discontinuity of the transformer in terms of impedance is gone. It means the moment you use per unit system, you just need this impedance, per unit impedance, to represent your transformer, and that is what we are doing when we are solving the problems. For representing your transformer, you just need this xt or zt, you can say. I hope you are getting this. So that is only possible if you neglect the shunt magnetizing branch. Is it clear? Do you understand the power of this tool, per unit system? How simple your system is going to become, how simple your circuit is going to become. Is it clear? Is it clear, beta? Tell me yes or no. Say yes or no. So we have talked about the per unit system also. Okay, per unit system also. So let us do some of the problems. Let us do some of the problems and then we'll proceed for the next topic. Okay, just do this problem very quickly. You have to be very fast, as if you are sitting in the GATE examination. You have to be very fast. He's asking a single phase voltage source with voltage 100 angle 130 degree. See, voltage 100 angle 130 degree delivers a current, and it is a source. So current is given as 10 angle 10 degree. He's saying calculate the real and reactive power and state whether the source delivers or absorbs each of them. It means you have to calculate the real and reactive power and you have to tell the nature, whether this source is supplying the power, real or reactive power, or it is absorbing. So if the voltage and currents are given in this form, how you are writing the complex power, beta? Voltage multiplied by the complex conjugate of the current. Very simple question. So it is 100 angle 130 degree. What is current? 10. Now angle becomes minus 10 because it is complex conjugate. Now if you multiply, it simply becomes 100 into 10 is 1000, and angle becomes what? 130 minus 10 is 120 degree. Is it clear? Sorry. Yes. So finally what you are getting as P and Q, tell me the values. Very easy. Just get it solved and tell me what you are getting as P and Q. So you will be getting, I'm directly writing here, minus 500 plus J 866. Now this is your real power and this is your reactive power. Because the real power you are getting as negative, so this is the power which is absorbed. This is the power which is absorbed. It is not supplied. Even if it is going to be a source, it is a source, it is a source. But the basic nature of source is to supply power, but you are getting P as negative. So as per our sign convention, as per our rule, negative means instead of supplying, it is absorbing this real power. But the reactive power you are getting, now this is volt ampere reactive. This is how we write the reactive power. And this is in watts, real power. So this much reactive power is being supplied by this source. Is it clear, everybody? Say yes or no. Don't be in a hurry. Don't be in a hurry. Okay, don't be in a hurry. See the next question. There is a voltage source. Voltage source is given as 141.4 cos omega t. And there is a load resistance of, it is something like this. Suppose this is a source and this source is supplying power to a resistance and there is one inductor. there is a resistance, and there is one inductor. So if you see the currents, if the total current is I, this resistance may be taking IR, this inductor may be taking IL. Okay. R is given as 10 ohms and XL, that is the inductive reactance, is given as 3.77 ohms. He is asking find the instantaneous power absorbed by the resistor and the inductor. Now you see, instantaneous power absorbed by the resistor. How we are writing it? Instantaneous power. If you talk about the resistor, can you tell me the current in the resistor? Can you tell me the current in the resistor? See, voltage is given as 141.4 cos omega t. It means this is the peak voltage. So what is going to be the RMS voltage? 141.4 divided by under root 2. This is nothing but 100. This is nothing but 100. Say yes or no. And suppose you are taking it as a reference, so you are saying it is 100 angle 0. Suppose it is 100 angle 0. You are choosing. So what is going to be the current in the resistive part? It is 100 angle 0 degree, and resistance is 10 ohms. It simply becomes 10 angle 0. This is the current you are getting in the resistor. What is the current you are getting in the inductor? 100 angle 0, 100 angle 0, and the magnitude of the inductive reactance is 3.77. So it is actually JXL. If you remove J, then you have to write XL, that is 3.77, and angle becomes 90. Angle becomes 90. Say yes or no. Are you getting this or not? If you solve this, tell me what is the value you are getting. I am just taking my reference so that we can save time. It is 26.53. 26.53. And what is the angle you are getting? Minus 90, simply minus 90. Now you see. So you got the current in the resistor, you got the current in the inductor. What is going to be the total current? IR plus IL. So it is going to be how much? You just solve it. I am giving you the direct value, 28.35. 28.35. Angle you are getting as minus 69.34. Minus 69.34. Now just see how I am writing the instantaneous power for the resistor and the inductor. Suppose I am writing it for the resistor. So there are two ways. Either directly you can write. Okay. Suppose I am writing the instantaneous power for the resistor. So I know that the resistor is only going to have the real power. So what is the voltage? 100. What is the voltage? 100. What is the current in the resistor? 10. It is 1 minus cos 2 omega t. So this is the expression for the instantaneous power in the resistor. Sir, what is the expression for the instantaneous power for the inductor? What is the voltage? 100. What is the current? Current in the inductor? Current in the inductor 26.53. 26.53. And it is only the reactive power which can be there for the inductor. So this is 26.53 sine 2 omega t, if you remember what was Q. I hope you are getting this. So it is 2653 sine 2 omega t. So one part of the problem is solved. You are writing the instantaneous power for the resistor as well as the inductor. Is it clear? Say yes or no. Are you getting this? Okay. Next he is asking, Next, he is asking the real and reactive power absorbed by the load. This you can do very easily. Networks, you must have done a lot of problems. The real and reactive power absorbed by the load. This is what you can directly just write. What is the real power absorbed by the load? Either you can write in terms of the resistor, because resistor is only going to absorb the real power, and reactive power you can write from the inductor, or directly you can use the RMS value of the voltage and total current RMS value, and you can use the cos phi and sin phi to find the values. Both are going to be same. So if you are writing real power, it has to be in terms of the resistor. So it is voltage, and what is the current? The current was 10. So it has to be 1000. What was the reactive power? Voltage 100. What was the current? 26.53. 26.53. So you are getting 2653. This is volt ampere reactive. If you want, you can directly find it, because you know what is the power factor angle. You have found the total current. So this is the power factor angle. From here also you can write. You can simply write what is P. You can write VI cos phi. Sir, what is V? 100. Sir, what is I? This I is not total I. 28.35. And cos of what? 69.34 degrees. Q you can write VI sin phi, or you can write 100 into 28.35 sine of 69.34 degrees. Both the ways you can do. Are you getting this? Everybody tell me yes or no. I hope there is no confusion. Okay. Is it clear? In the last, he is asking the power factor. Now, power factor is nothing but cos of the relative angle between the total voltage and total current. So, simply cos of what? Cos of what? This angle. Cos of what? This angle. Cos of this angle. Cos 69.34. Just find it. What is the value you are getting? Cos 69.34. 0. What you are getting is the power factor. So power factor you are getting as cos of 69.34. It is coming 0.3528. 0.3528, and this is lagging. This is lagging. Is it clear? Because the current is lagging the voltage, so it is lagging. I hope it is clear. Everybody say yes or no. Anyways, just do this problem. This problem is related to the per unit system we have discussed. A single phase 10 kilovolt 200 volt generator. So generator is something like this. Internal impedance ZG. Suppose this is the internal impedance. This is the internal impedance. This is the generator. This is 2 ohms. Okay. Using the ratings of the generator as base value, okay, determine the generated per unit voltage that is required to produce a full load current under short circuit condition. Under short circuit conditions means what? The terminals have been shorted. If the terminals have been shorted, how much current you are getting? Can you tell me? What is the current in this condition? What is the current in this condition? Full load current under short circuit condition. Full load current. So what is the voltage? Sorry, what is the total kVA? 10. So it is 10 multiplied by 1000 because it is kVA. Simply divide by the voltage. So this is what you are getting as 50. So 50 ampere you are getting as the full load current in case of the short circuit, when the terminals are short circuit. Now when there is a short circuit, whatever voltage is generated, that voltage is actually consumed by the internal impedance of the generator only, because there is no other impedance in this circuit. Yes or no? So EG becomes what? EG becomes I into ZG. I is 50. What is ZG? 2. So it is 100. but this is 100 volt. He is asking per unit. So it becomes 100. What is the base voltage? 200. So it becomes what? 0.5. So 0.5 per unit is the generated EMF required to circulate no problem, it's okay. They can see it later on because we have lot of sessions together, so we cannot avoid overlapping because of the shortage of the time. So that is the reason we have to abide by some of these glitches, and we have to just cover it as and when you get the time, you can just observe it. Okay. Okay. So we'll do some more questions later on. Now let us talk about so we have completed the basic fundamental parts. We have covered the per unit system, and this is the area from where you can expect at least one or two questions, and this is very fundamental, which you are going to use if you're going to solve further problems. This is one thing. Now I'm going to tell you something about the transmission line. Now when you talk about the transmission line is nothing but a conductor. It is nothing but a conductor. Say yes or no. It is nothing but a conductor. And we are generally using aluminum. You all know we are generally using aluminum. We are not using copper. What is the reason why we are not using copper? Can you tell me? Just tell me in the comment section. Let us make this discussion little light, because continuously for last 2 hours we are discussing things. So let me ask some questions from you guys. Why we are using aluminum? Why we are not using copper? What is the main reason? What is the main reason? Tell me yes or no. Why we are using cost? It is one of the reasons. There is one more important reason. Cost for engineers, for anything, the reason is cost. Yes, because engineering is all about optimizing the system, economy. Yes or no? So cost is going to be answer for everything. Now please understand why we are choosing aluminium over copper. Can you tell me what is the resistivity of copper? 1.68 micro ohm centimeter. Just cross check it if I'm not wrong. What is the resistivity of aluminium? It is 2.65 micro ohm centimeter, if I'm not wrong. If I'm not wrong. Now if I compare the resistance of aluminium, so it is going to be rho L upon A. So this is aluminium, this is aluminium. Suppose length we are taking same for both the cases, for copper also, for aluminium also. So if I write the resistance in case of copper conductor, it is rho copper. Length we are taking same for both the conductors, and this is the cross sectional area if we are using the copper. For comparing these two resistances, if I put the condition RAL is equal to R copper, this is rho AL into L upon cross sectional area in case of copper. This is rho copper L upon A copper. Length we are taking as same, so this is cancelled. Now you are saying the resistivity of aluminium is higher than the resistivity of copper. So this ratio can only be exactly same if the cross sectional area of the conductor in case of aluminium is going to be more than the cross section area in case of the copper conductor. Say yes or no. It means if you're going to see for this particular condition, if you're going to see your conductors are going to look something like this. Your conductors are going to look something like this. It means what? This is your aluminium conductor and this is your copper conductor. Now aluminium conductor cross sectional area is large. cross-sectional area is large, it means what? The electric field stress is going to be comparatively less. The electric field stress is going to be less in case of aluminum conductor in comparison to the copper conductor. So in this case, corona is going to be less in case of aluminium in comparison to the copper conductor. Now corona is going to be a very important phenomena, and the losses are going to be very significant when you talk about very high voltages and when you talk about very long distance, long transmission line. So when you talk about long distances, long transmission line of very high voltage, the losses due to corona becomes very significant. So this is one important reason why we don't go for copper, we go for aluminum conductors. There are some other reasons, as Ashish has mentioned, that cost is one reason, availability, aluminum is available in abundance, that is the one reason. Weight density ratio is one reason. If you see the weight of the aluminum in terms of its density is going to be comparatively very less. So if the weight is less, the sag of the conductor is less. If the sag of the conductor is less, the ground clearance required is more. So the height of the tower is less. Overall, you can say there is a saving in the system. Overall, you can say there is a saving in the system. Everybody is getting this? Say yes or no. No, copper is giving you more conductivity, but still we are using aluminum because of these reasons. Because of these reasons. Is it clear, everybody? Now we understand that our conductor medium is going to be aluminum, that is sure for us. Now when we are designing our transmission line, there are certain types of conductors which we can use. There are certain types of conductors which we can use. The first one is single solid conductor. The first one is single solid conductor. The second one is stranded conductor. Stranded conductor. Third one is bundled conductors. Bundled conductors. The fourth one is hollow conductors. Hollow conductors. Now let us see one by one. Okay, very quickly we are going to go through this because we have to discuss a lot of things. The first case, single solid conductor. Single solid conductor. It means you don't apply your mind, simply have a circular cross section. Simply have a circular cross section and just one conductor you are having for your transmission line. Now, biggest problem for this case is what? Biggest problem I'm saying, the biggest problem is skin effect. What is the biggest problem? The biggest problem is skin effect. Skin effect is going to be high. What is the biggest advantage? Tensile strength is going to be very high. Tensile strength you understand, na? Tension you can understand. Tension in a wire, tension in a string you can understand. At any point if you touch, the forces are towards both the sides. So it is a tensile strength. Tensile strength is high. Now skin effect is a big problem for us. Because skin effect, what is the problem? The AC resistance is more than DC resistance. When resistance is going to be high, losses are, when resistance is high, so losses are high. Yes or no? Efficiency of power transmission is going to be very less. Most of the power is wasted in the transmission system itself. That is what we want to avoid. So we want to reduce skin effect. How we can reduce the skin effect? Now please see. Please see this. If you have two conductors, if you have two conductors, okay, if you have two conductors and suppose the depth up to which current is present is going to be same for both of them. What is the meaning of depth up to which current is present? What is the meaning of depth up to which current is present? This is nothing but skin depth. This is nothing but skin depth. The effective current up to the distance from the surface, the distance up to which the effective current is present, that is what we'll discuss skin effect also, don't worry, we'll discuss, okay? We'll talk about ACSR also, don't worry. If this skin depth is going to be same and we are reducing the diameter of the conductor, if we are reducing the diameter of the conductor, then what is happening? Skin depth is same. Skin depth is same. It means if you reduce the diameter, the non-uniformity of current distribution across the cross section is reduced. Hello. If you reduce the conductor diameter, the non-uniformity in the current distribution across the cross section of the conductor is reduced. There is more non-uniformity. There is less non-uniformity. It means you can say in this conductor, the skin effect is less. And in this conductor, the skin effect is more. Sorry, reverse I have written. Sorry. Here skin effect is very high. Here skin effect is less. So instead of using one single solid conductor, we are using a smaller diameter strand, and that is what we call as a stranded conductor. And that is what we call as a stranded conductor. That is what we call as a stranded conductor. Stranded conductor means something like this. Something like this. Maybe I'm not able to make it much ideal, but I hope you can correlate. So instead of using one single solid conductor, we are using multiple strand. Okay, I hope it is clear now. Now you see what we have done. See very carefully. This is what we call as a strand. This is what we are calling as strands. So instead of using one single conductor, we are using smaller strands. So what has happened, sir? What has happened, sir? Number one, skin effect is comparatively reduced. In comparison to the previous case, skin effect is reduced. So we are happy. But there is one big problem. गए थे हरि भजन को ओटन लगे कपास. When you solve something in such a way where a solution is asking for a new problem. So you are going for solving the problem of a skin effect. You have solved it. But there is one new problem. What is that? For sharp corners, the electric field stress becomes very high. Whenever you have sharp corners or irregular surface, the electric field stress becomes very high. The moment electric field stress becomes very high, the possibility and intensity of corona becomes very high. So we were looking for solving the skin effect problem. We got a new problem of corona. So here corona becomes high. New problem. This is a new problem. There is one more disadvantage. Instead of one single solid conductor, if you are having multiple strands, the tensile strength is going to be weakened. Tensile strength is also gone. Babu, tensile strength is also gone or has become less. When tensile strength has become less, it means what? It means what? Hello? It means what? Bolo bolo, tell. If tensile strength is reduced, what is going to happen? Very common sense question. I want to show you just. Very common sense based question. Very common sense based question. Just see this. This should be the ideal positioning of the conductor. But when the tensile strength is reduced, conductor is like this. So what happened? The sag of the conductor is increased. When the sag of the conductor is increased, what happened to the ground clearance? What happened to the ground clearance? The ground clearance is reduced. Ground clearance reduced means there is a danger. There is a danger. Your girlfriend may be going below this high voltage transmission line. Very dangerous. What to do? Sir, we have to increase the height of the tower. Sir, we have to increase the height of the tower. Increasing the height of the tower means what? Cost. Cost becomes high. Cost becomes high. Say yes or no. Now you see. When we talk about the stranded conductors, for stranded conductors, there is one solution. What is the solution? One is homogeneous stranded conductor. One is composite stranded conductor. The homogeneous conductor means all strands of aluminum. We call it AAC, all aluminum conductor. When we say composite stranded conductor, it means there are some steel strands along with aluminum strands. And what is the purpose of having the steel strands? To increase the tensile strength of the stranded conductor. This conductor we are defining as ACSR conductor, steel reinforced aluminum conductor. Steel reinforced aluminum conductor. I hope it is clear. Now for composite conductors, always remember, if it is written like 7/30, always the smaller number of strand will belong to steel, because steel is not going to carry the current. Only the aluminum strands are going to carry the current. Okay, so this is the way how we represent ACSR conductors. Okay, number of steel strands, number of aluminum strand, or number of aluminum strand and number of steel strands. Always the lesser number of strand will belong to the steel. Is it clear? Now you see, if you talk about the stranded conductor, listen, very important. If you talk about the stranded conductor, okay, this is the core strand which we are calling as layer number 1. This is what we are calling as second layer. Second layer, you are having how many strands? 6. So the pattern is, first you are having the core strand, after that the next layer you are having 6, then you are having strands in the multiples of 6. 6, 18, 24, 30, 36 and so on. Okay, so this is how this pattern goes on. At the core you have 1, the next layer, second layer, you have 6. Suppose you are asking total number of strand, so that is equal to 3n square minus 3n plus 1. 3n square minus 3n plus 1, where n is the number of layer. It starts from 1, 2, 3, 4. As many layers you are having, you can find the total number of strand. Is it clear? Everybody tell me yes or no. Sorry. Is it clear? If you see the diameter, that is 2n minus 1 into d, where d is the diameter of the individual strand and n is again the number of layer. But please remember how you are defining this number of layers. Okay, please, one question I'm going to give you, if you can just solve it so that you can remember these discussion. Just give me a moment. I think that question we have missed. Okay, no problem. So let me just give you that question. Let me just give you that question. Okay, just do that question. I'm giving you that question. Okay, I'm asking, a stranded conductor is having 6 layers. Now tell me the total number of strands. Total number of strands. Tell me the total number of strands. So what formula you're going to use? 3n square minus 3n plus 1. Just put the value of n as 6. Put the value of n as 6. 6 layers means what? Sir, this is first layer. Sir, this is what? Sir, this is second layer. Then you have, after 6, you have 12. You have to count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In the multiples of 6. Are you getting this? Just put the value of n as 6, you will get the total number of strands. I think it is coming as 91. You must be getting it as 91. Avinash is saying ACSR conductor or zebra conductor. Okay. Listen. So I hope this is okay for all of you. ACSR conductor, these small things okay for you. Now, let us go for the more important one, that is the bundled conductors. Bundled conductor. Sir, what do you mean by bundled conductor? Bundled conductor means that instead of, listen. Instead of using one conductor, we are using a smaller size conductor, but giving them some spacing. For example, if you are saying, sir, this is radius r. Okay, this is having voltage V, current I. Now you are saying, sir, this is R1 radius, this is R2 radius, this is R3 radius, and like this. Suppose n number of. Now, in case of bundled conductors, these smaller conductors we are calling as subconductors. We call them subconductors. Now, suppose we are saying the current is divided as I1, I2, I3, and up to, suppose this is IN. Yes or no? But all these subconductors are connected in parallel, so voltage is going to be same for all of them. Now, if you apply the current rule, okay, if you apply the current rule that this total current should be equal to the individual current of the subconductors, so you can write like this. Now, for the transmission line, you know that current density is constant. Current density constant means what? What is I? J multiplied by A. Current density multiplied by the cross-sectional area. Now, if current density is constant, it means current is directly proportional to the cross-sectional area of the conductor. Sir, what is cross-sectional area of the conductor? It is pi r square. Pi is a constant. It means current is directly proportional to the square of the radius. If you put it here, so you are simply writing r square is equal to r1 square R2 square up to Rn square. Now, if I am saying all the subconductors are having the same radius, and this is equal to Rb, B represent the bundled conductors. So I can write R square as n times Rb square. So from here I can write the bundled conductor radius is R upon under root n. Note down this formula, important, can be asked. Madhu is saying, sir, how tensile strength is less in stranded conductors? Here volume is same for single and stranded conductors. See, what is happening is one conductor was like this. What you have done, you are using multiple strands and they are twisted. But how much you twist it, how much you manage it, but still the tensile strength is gone. Are you getting this? You imagine you are having a string having some radius. Now you divide it into 10 smaller radius strings and just try to intertwine them. You will understand, logically, common sense, you can understand that tensile strength is reduced or weakened. Madhu, are you getting this? Tell me yes or no. Are you getting this? So this is going to be the radius of the subconductor in case of a bundled conductor system. Now I want to understand what advantage this bundled conductor system is going to give us. Now you see, actually your bundled conductor system is doing what? See what it is doing. So if this is your transmission tower like this, suppose this is your transmission tower. Now for a three-phase circuit, suppose this is what you are having. Now see, what he is doing, for A phase, it is having A1, A2. For B phase, not one conductor, it is having two conductors, B1, B2. Similarly, for C phase, it is having C1, C2. Now you see what they have done. They have maintained a distance between the two smaller size conductors. Sir, what is the advantage of this? Suppose I calculate the GMR for a conductor. We'll talk about geometric mean radius later on, okay? First you understand. That much you must be knowing. So how I'm writing this? I'm writing GMR A1 multiplied by GMR A2 and power 1 by 2. But if you see A1, A2 are going to be symmetrical for each other, it means GMR for A1 is same as GMR for A2. So you can simply write it as either GMR for A1 or GMR for A2. Suppose I am writing GMR for A1. It is going to be 0.7788 multiplied by the radius and multiplied the distance between A1 and A2, that is S. How many distances? 1, 2. What is power? 1 by 2. Now by introducing this small distance S in case of bundled conductors, what you have done? By introducing S, you have increased the GMR. Sir, what happened by increasing the GMR? The electric field stress at the surface of the conductor is given as phase voltage divided by GMR ln GMD upon GMR. Now you see, if you are increasing the GMR, the electric field stress at the surface of the conductor is reduced. It means the possibility and intensity of corona is also reduced. So by introducing the bundled conductor system, actually you have overcome the problem of corona to some extent. I hope you are getting this. Say yes or no. Now what has happened? What is the advantage? See, sir, what is inductance? Sir, what is inductance? Sir, it is 0.2 ln GMD upon GMR. We will discuss this formula later on when we will talk about the line constant calculation. Sir, this is millihenry per kilometer. Sir, you are saying GMR is increased. Sir, GMR increased means L has reduced. Oh ho ho. Sir, what about capacitance? 2 pi epsilon naught upon ln GMD upon GMR. Sir, GMR you are saying is, sir, increased. So this ratio reduced. This ratio reduced means capacitance has increased. What about the surge impedance under root L by C? I am telling you the consequences of introducing the bundled conductor. Sir, L has reduced, C has increased. It means surge impedance has also reduced. Sir, what about surge impedance loading? It is V square upon ZC. Sir, surge impedance is reduced. It means surge impedance loading has increased. It means balle balle. Everything you are getting as advantage. Everything you are getting as advantage. Avinash, you are here to take my interview or you want to learn? Okay. I can tell you what I know. If that helps you, then it's my luck. Maybe your luck. Okay. So don't try to deviate the class. It gives a very bad impression that we are, as a unit, as a team, we are discussing something and suddenly you are jumping into this and you are saying, oh sir, what is this? Oh sir, what is it? It's not a mature behavior. It doesn't go right in a right way. Okay, so be mature. If you have any doubt, then you can just join my Telegram channel. Whatever doubt you have, please tell me. I will definitely help you out. As far as your question is concerned, let me answer this. See, ACSR conductors, why we are using? ACSR means steel reinforced aluminum conductor. It means we are using number of steel strands to increase the tensile strength. If you increase the tensile strength, the sag in the conductor is reduced. The sag in the conductor is reduced, so ground clearance is increased. Ground clearance is increased, so the height of the transmission tower is reduced. If the height of the transmission tower is reduced, the overall cost is reduced. Okay. No, that we will discuss. Okay, don't worry. We are writing here for understanding purpose. We are writing here as GMR. It is not actually GMR. In case of capacitance, we don't have internal flux linkage. Are you reading this? In case of capacitance, it is electric field. We don't have internal flux linkage. Na? Electric field cannot exist inside the conductor. So for that purpose, it is not actually GMR. See, understand, it is not actually GMR, but it is like GMR. As you are saying, it is physical radius. No, it's not physical radius. I will tell you. I will prove it. You can say it is physical radius only if it is a single conductor. If it is any other conductor, if it is stranded, if it is bundled, you cannot say this. The GMR in case of capacitance is GMR as you calculate for inductance without the factor 0.7788. Rest everything is exactly same. Rest everything is exactly same. I hope you are getting this. One more thing, if you talk about the power transmission capability, suppose it is mod V1 mod V2 upon X sin del. I hope you know this. Now you are saying, sir, L is reduced. If L is reduced, X is reduced. If X is reduced, suppose this is constant. For constant power transmission, if Now if x is reduced, this value is increased. So this value has to reduce. This value has to reduce means del has to reduce. Del has to reduce means del is going to have a smaller value. Now a smaller value of del means what? Higher stability. It means what? Higher stability. It means what? Higher stability. Is it clear? Everybody just tell me in the comment section, are you getting this? Are you getting this or not? Say yes or no. Madhu, are you getting this? Madhu, Ashish, Abhinash. Tell me, are you getting this? Okay, so this was about the bundled conductors. Okay, now let us talk about the concept of GMD and GMR. Hollow conductors is not going to be asked in your examination. You can just leave it. But for the understanding purpose, you can understand that instead of having a solid conductor, in case of hollow conductors, we are simply using number of strands at the periphery of a circle, at the periphery of a cylinder. That is what we call as hollow conductors, but for your GATE examination, that is not required. But understanding the concept of GMD and GMR is important. So let us talk about the concept of geometric mean distance. Geometric mean distance. Now first you understand what is this geometric mean? Why we are talking about geometric mean? Today we cannot go up to fault. Revens, Bagachi. Okay, we'll talk about fault, relays, all this most probably in the tomorrow's class. Okay, so we'll have 3 sessions for power system. Today is one session, tomorrow also, and then another session we'll plan. So we'll have 3 sessions because we are going in a flow. We are going in a flow. The starting chapters will take more time. As you move on, the later on chapters will not take that much time. Okay, because there you directly understand the logic, formula, do some problems, you will be done. But starting, we have to make some base. That base is required. Anyways, let us understand what do we mean by this geometric mean. The logic is, the idea is, suppose you have a 3D object. Suppose it is a 3D object. And suppose it is a point. Suppose it is a point. Suppose this is a point, suppose this is a point. This is a point, this is a point. This is a point, this is a point. I am asking what is the distance between these 2 points? You just measure it and tell me. But the moment I ask you, what is the distance between this 3-dimensional object and this point, you will be just scratching your head. Sir, I have to calculate distance from which point? So the concept of geometric mean is telling you that don't worry. What you do, you just take infinite points on this 3-dimensional object. You take infinite points on this 3-dimensional object, and all these infinite points you connect with this point. All these infinite points you connect with this point. So you will get infinite distances. What you will get? You will get infinite distances, and all these infinite distances, you just find the geometric mean. You just find the geometric mean. Power system, you can expect somewhere around 8 to 12 or maybe even up to 14, 16 marks you can expect, because this is one of the core subject. Okay, one of the core subject. Any subject, why you are taking it lightly? Okay, when you eat something, have you ever said, okay, I will eat less? No. If you are eating 4 chapatis, 4 bread, have you ever told, okay, today I will eat only 2? No. When you are playing something, when you are enjoying something, how you can restrict? And you are going for GATE examination, something which is the most important or crucial part of your life right now. Rest everything is secondary. How you can take a risk? Even if it is one question, one number, one mark, you have to fight it like anything. I hope you're getting this. It's not just one subject, any subject, my dear. Don't take it lightly. It's about your career. So I hope you understand. The idea is for a three-dimensional object and one point, if you want to find the distance, take infinite points, take infinite distances, take their geometric mean. I hope you're getting this. Now what is happening? Geometric mean distance. What is happening? Suppose you have a single phase. Suppose you have a single phase two-wire system. Single phase two-wire system means one wire the current is going, one wire the current is coming back. One wire the current is coming, one wire the current is going back. Okay, so we call it single phase two-wire system. We call it single phase two-wire system. Say yes or no. So let me just draw it a little faster so that we can discuss it. Now you see, suppose you have two groups of conductor. We can call it two groups of conductor also. You can call it group A. You can call it group B. Okay, you can call it group A. You can call it group B. Suppose this is 1, 2, 3 and up to m number of conductors. Suppose here it is 1 dash, 2 dash, 3 dash and suppose it is up to n dash. So m conductor in group A, n conductor in group B. When you say geometric mean distance, it means simply you want to know the effective distance. Effective distance. And when you talk about GMD, you always talk about the distance between two different groups of conductors or two different phases. Always between two groups or phases. It means it accounts for the mutual flux linkage. If it is only one conductor, you cannot talk about geometric mean distance because it is always in between two groups of conductors or two phases. It can never be for just one conductor or only one conductor. It's not possible. So mutual flux linkage is the distance up to which mutual flux linkage are present. Now you understand. Actually, when you say GMD, you want to know what is the effective distance between this and effective distance between this. Now again, you are scratching your head. It is not just one point, how you find the distance. So I am giving you one solution. You take conductor number 1 here. Listen now coming the climax of the movie. You hold conductor number 1 of this group of conductor and take its distance from all conductors in the other group. 1 1 dash, 1 2 dash, 1 3 dash, 1 n dash. Then you go to conductor number 2 and find the distance between 2 1 dash, 2 2 dash, 2 3 dash up to 2 n dash. It means each and every conductor in group number A, you see what are the different distances of that conductor from all the conductors in the other group. And how many distances you are getting? Just take the effective root. That is geometric mean. Hello. Suppose I want to write GMD for this group of conductors. So GMD always finding two different group of conductors A and B. So actually I am finding the effective distance between A and B. So what I am doing, hold conductor number 1 and see its distance with all other conductors in group B. So what I am having, just see this. I am writing conductor number 1. In group A, I am writing conductor number 1. So it is D11 dash, D12 dash, up to D1n dash. Now this is for conductor number 1 in group A, but you have to write for all the conductors in this group. So now I am writing for conductor number 2. So conductor number 2 I am writing D21 dash, D22 dash, D2n dash, and you have to do it for all the m conductors in this group, all the m conductors in this group. So I'm writing dm1 dash, dm2 dash, up to what? dmn dash. Now I want to ask you, now this is going to be your childhood problem, your childhood problem. When you wanted sweet mithai, but guests are sitting in front of you, so you are waiting when they will go and you can eat the sweet. Remember your childhood? Now understand from that point of view. There is one box of sweet. How many sweets? How many sweets in this box of sweets? How many sweets? From 1 to n dash. So n number of sweets. How many such boxes you have? How many such boxes you have? M. Can you tell me total number of sweets? M number of box. N number of sweets in one box. M into n. You want one sweet? Sir, yes. What is the effective root? 1 upon mn. Finished. This is GMD. This is GMD. Yes, definitely we are coming with the PYQs also, don't worry. See, every faculty on Geeks for Geeks platform, they are so well experienced that before you think of the problem, that what problem is going to happen to you or you can experience the problem, we already have a solution. We have faculties who are 15, 20 years of experience they are having in this field. So don't worry about this. What we are giving you, okay, what we are providing you is already optimum, best. First theory, then PYQs, then formulas, then Tathastu. Vijay Bhava. Madhu will talk about it, okay? You have to wait for it. This is not extempore, or you can say just, are you getting this? We cannot just have one-to-one discussion out here because a lot of people are going to be benefited with this session. I know that. I know that. So I hope you got the idea about the GMD. Yes or no? Okay. Now let us talk about GMR. Geometric mean radius. So when I was talking about GMD, I was talking about effective distance between two groups of conductors or two different phases. But when I say GMR, GMR is always calculated within the same group or within the same phase. It means we are talking about radius. So we are talking about effective radius. We are talking about effective radius. We are talking about effective radius. So it is always calculated within the same group or within the same group or phase. Within the same group or phase. Now see this, something really important. It means for this group of conductors, single phase 2-wire conductor system, if you are having group A and group B, it means if I am calculating GMR, I will calculate GMR for group A and GMR for group B differently. Are you getting this? Are you getting this? Suppose I am talking about GMR for A. Suppose I am talking about GMR for A. GMR for A. How I am calculating? Just see this. When you say, sir, what is the effective radius of this group A conductor? Because there are a number of conductors. Their radius is going to be also different. Suppose all are going to have same radius, but their distance is different. Distance between 1 and 2 is different. Distance between 1 and 3 is different. And distance between 1 and m is different. Sir, how to find its effective radius? Now see, find the effective radius of conductor number 1 multiplied by its distance from all other conductors in the group. This is one part. Then again, take conductor number 2, write its effective radius, and then multiply its distances from all other conductors in the same group, and keep on doing it for till the last conductor, and then find the effective root. Finished. Suppose I am writing it for GMR for group A. So first I will go for conductor number 1. So what I am writing? The effective radius of 1. So it is 0.7788 R multiplied by distance between conductor number 1 and all other conductors in this group. So distance between 1 and 2, 1 and 3, 1 and 4 up to 1 and M. So how many distances I am writing? Distance between 1 and 2, distance between 1 and 3, distance between 1 and M. Similarly, I am writing for conductor number 2 in group A. So effective radius of conductor number 2 and then its distance with 1, its distance with 3, and keep on doing it for its distance with conductor number M. Now you have to do this up to the last conductor in group A, that is mth conductor. So it is effective radius of the mth conductor multiplied by dm1, dm2, and do it up to dmm. Sorry, dmm minus 1. Now you tell me. Again the problem of sweets of your childhood. How many sweets are there in one box? M sweets. M sweets. How many sweets are there in one box? M. How many such boxes? M. Total how many sweets? M square. How many sweets you want? Sir, 1. What is the effective root? 1 upon M square. So this is all. Yes, we'll bring engineering services course also, don't worry. So this is all for today's session. Okay, so let's stop here. We are going to continue the further discussion in the next class. Okay. So tomorrow we are going to start where we are leaving right now. And I hope that we'll try to cover many new important topics for your upcoming GATE 2026 examination. So if you want to connect with me, if you want me to help you in your GATE preparation, if you want that I can just be significant in that, you can join my personal Telegram channel, that is Ashutosh Sir. Okay, so we have already launched some of the courses on Geeks for Geeks platform that you can see, and if you find it suitable for you, then you can go for it. So let's meet in the next session tomorrow when we are going to discuss some more important concepts for your favorite subject, power system. Till then, goodbye, take care, all the best. Thank you so much. Thank you everybody, take care. Yes, we'll discuss fault and stability tomorrow. We'll discuss each and everything, okay? We'll discuss fault, stability, everything tomorrow, don't worry. Is it clear, everyone? We'll do some questions also. Is it clear? Tell me yes or no. Happy? So this is all. Good night. Take care. See you tomorrow. See you tomorrow. Good night. Good night, everyone.